Hello dear all, welcome to the Static Power Conversion 1 course. Today we are going to discuss the switching parasitics and how to deal with them in our converter circuits. So let's begin with the definition of our converter that we are going to talk about. We have plotted here a synchronous DC-DC converter where two switching components, actually two MOSFETs, are connected in series, which constructs a half bridge, and we have placed an L and the C components, and so this is actually a buck converter circuit where the input is given on the left hand side, and we have modeled the outload with the current sink with 10 amps as a load. So on the left hand side here are our PWM sources, the source for the PWM source for the top side switch and PWM source for the low side switch. So this is a buck converter, as I said before. However, this is called as synchronous buck, synchronous DC-DC converter, because we replaced the diode, which should have existed here, with a MOSFET to conduct the current, the freewheeling current through this switching component. So actually this is a bidirectional DC-DC converter. Consider that we have placed our DC source, the input voltage, to in the place of the load, and we have placed the current sink to the side of this input voltage. So this can work as a boost converter as well, because of the replacement of this diode with a switching component MOSFET. So we are going to construct a gate driver structure on this converter board. But first, let's start with the definition of dead time. As you see here, we have plotted the output voltage and the line the current of the inductor. This converter operates with 75 kilohertz of switching frequency, where the duty cycle is equal to 0.5. So when we look at the gate source bias voltage of the top side switch and the low side switch, the black one is the top side switch and the blue one is the low side switch. The source board name is connected to ground, so it is not shown here. It operates inversely. What I mean is that when the high FET turns on, the low FET turns off, and it's built for vice versa. However, we see that here, whenever the top side switch turns off, immediately at that moment the low side switch turns on, and it's also valid for the other transition period as well. However, in practical circuit, this causes problems. We are risking our circuit by causing a turn on simultaneously for high and low side switches. So in order to prevent a short circuit failure, we always provide a small amount of blank time, which is called as dead time or dead band, to increase our safety and reliability. However, this comes with a disadvantage, as it is written on the left hand side. Dead time or dead band causes a voltage drop on the output because it reduces the effective duty cycle of our applied pulses. So here we see a difference for the average voltage. It was 24.8 in the previous case. However, it's now reduced almost 23 voltage. This is the effect of dead time. However, we need this period for safety. The dead time is quite interesting to be investigated, because here the important transitions occur. What I mean is that since we have an inductive current, which means that this current is continuous during the whole operation, the switching period is the duration when the current commutates from high FET to low FET, or when the current commutates from low FET to high FET. During this transition, we observe some voltage change. For example, let's say the top side switch is turning on, so its voltage is reducing. At the same time, we observe that the low side switch voltage turns on, because their voltage sum is equal to our input side voltage. And we are seeing that at that moment the current makes some overshoot, and it causes increased switching loss on our switching components as well. I would like to draw your attention to something here important. When we look at the bottom side switch, when it's turned off, actually nothing changes at that moment. However, whenever the gate top voltage is increased, the transition occurs at that moment, and it is also valid for the other edge as well. So this is because that here the circuit is controlled by the high FET switch. It regulates the current actually, and the low FET switch is there just for freewheeling. So the main control is done by the high FET switch, and in this circuit we are calling the high FET switch as control switch. However, the low FET side is just working in synchronous with the other switch, so it is called as the synchronous switch. However, this is not valid for whole circuit. We cannot say that the high FET MOSFET is always a control switch. It totally depends on the freewheeling and the controlling periods. And let's say this circuit was operating in the reverse direction. I mean, we have connected here a voltage source, and a load is connected instead of this voltage input. So this means that our freewheeling circuit, freewheeling switch is now high FET. So this would be called as synchronous switch. So things get important here, that the output capacitance of the MOSFETs. As I said before, here the transition period is showed in a zoomed view. The current increases quite a lot. This is because that at that moment the output voltage, output energy stored on the output capacitance of these MOSFETs actually need to be charged or discharged, and this current, this surplus current actually charges or discharges the output capacitances of our switching components. Let's consider a circuit in a more realistic way. The circuit is not ideal, so the connections of these MOSFETs and the source always include some resistive and inductive components. More important than the resistive component, inductive component causes significant loss, a significant increase in the power losses, and as well it causes some oscillations. Let's see the moment when the high side switch is turned on, the gate voltage is increased as shown here. At that moment we see a clear oscillation on the bottom side switch, drain to source voltage, and we observe the same oscillation on the drain currents as well. When we check the other transition period, let me show it in the better way. The oscillation voltage now, the overshoot voltage, actually exceeds the 140 volts. However, the transistor used here, the EE463 are rated with 100 volts. So this means a over voltage breakdown for our switches. So we need to solve this problem before starting of implementation this circuit board. Moreover, these oscillations on the voltage or the current causes some problem. As I described just before, the over voltage breakdown is caused by the voltage oscillation, and since we see an increase in the voltage and the current as well, this causes a higher switching loss dissipation on our switching components. And more importantly, it causes the EMI problems, which means that our circuit radiates to the which couples to the other circuits like analog measurements, the digital signals, etc., and it distorts the other signal around them. An example of EMI problem actually shown here. I mean, it is just a magnet, but the magnetic coupling with the analog and digital signals inside this screen or the television causes some change in the color and the variation on the image. So we need to solve these EMI problems in our circuits. On the right hand side, we are seeing a three-phase circuit. The phase A is given here. It is a half bridge. Three half bridges are connected in parallel with the same DC link voltage here. You see here an explosion which caused a black powder around these switching components, and we have seen another problem on the right hand side at the phase B. As you see, there is a gel inside these switching components, just to keep all components inside this package. When it gets exploded, it is actually provided by the manufacturer for the safety. So actually there are three ways to shrink these ringings or solving these problems. The first thing you can do is the slowing down the gate driver speed. So we need to pay some attention on gate driver designs. We can use a snubber circuit to reduce the speed of transition moments, and a better way is actually to eliminate the high inductances on the power loop or the gate loop, which will be defined soon. So let's begin with the gate drivers. We were told that the gate of the MOSFETs is actually includes a capacitance which results in no current flow through the gate pin. However, this is not valid for the actual case. The gate signal, when we provide some gate bias voltage between the gate to source, we actually accumulate the positive charge on the gate pin, which results in accumulation of electrons, free electrons, on the channel. So by this method, we are actually turning on this MOSFET or the IGBT to conduct some current. However, here you see that there is a metal oxide insulator, which means that when we put here a component, a conductive component, and if we place another conductive component here, which I mean the electrons, the isolation barrier between these two conductors actually causes some capacitive coupling. So we model this capacitive coupling from gate to source, and it is called as CGS. And we model this parasitic capacitance as from gate to drain, and it is called as CGD. And by the way, it is named as Miller capacitance as well. And we have another capacitance from drain to source, and it is called as CDS. And the proper definitions of input capacitance is actually the sum of gate to drain and gate to source capacitances. The output capacitance is the sum of the drain to source and gate to drain capacitance, and the transfer capacitance is just equal to gate to drain capacitance or the Miller capacitance. The capacitive couplings can withstand with the DC bias, DC current. They do not make any current flow if it is a DC. However, when a transient current is applied, whenever the voltage between this gate to source is changed, actually by d VGS dt, it causes some current flow through the gate source capacitance. So actually we cannot say that the gate is not conductive. It conducts current if it is AC and if it is transient. So we measured the gate currents for turn on or turn off moments, and it is seen that the gate is either supplies or sinks current with amplitude of 3 amps, which can be considered quite high to be supplied by a microprocessor or microcontroller, or the Arduino, etc. So we know that the typical digital controller current limit is 100 milliamps, which means that our digital controller cannot supply this current, and this current should be supplied with another component which is called gate drivers. So there are two common gate driver types, which one of them is constructed with MOS switches and which one of them is constructed with the BJT amplifiers. So here actually you connect this input port, the MCU, the microcontroller port, to your digital controller, and this pin is connected to the gate of the switching component, and the main current is actually supplied through the source of through the external voltage source. So let's see it in a real circuit on the simulation. Now we have replaced the PWM source between the gate to source bias levels of high FET and the low FET with the gate driver modules. So we see we modeled a PWM signal, and it is called as the microcontroller output for the bottom side switch, and this bottom side switch is connected to a MP type of bipolar gate driver structure, and we have placed a voltage source to supply the required current for driving the gates, and the middle point, the switching node, is actually connected to gate pin of the switching component, and this is valid also for the top side switch as well. So now we have measured the supplied current by the microcontroller. So the microcontroller now just supplies the current in maximum 30 milliamps, which means that we have reduced the current stress on our microcontroller, and the main current is actually supplied by the gate driver power supplies. Okay, we actually like and we use generally this type of gate drivers because they are very robust and useful. However, there is a problem. As you see that the microcontroller here, since we modeled the microcontroller with the PWM voltage source, they have different ground pins. However, this is not valid for the actual case. These grounds should be should be connected to common signal, which means that our high side switch should be isolated or supplied with another type of power source. Otherwise, this type of gate driver circuits costs a lot if we consider a mass production of a converter. So what we are gonna do is to change this high side power supply, the gate driver power supply of high side switch, with a bootstrap circuit. Now we do not need to connect another power supply to here, because the current is actually supplied with the low side gate driver power source. So let me explain how it works. Let's say we are turning on the low side switch. I mean, we have applied a high pulse to the gate pin of our low side switch, which means that the voltage between these two, the drain and the source, is reduced a lot. So this actually activates a current path from this power supply, and it conducts through the diode, the resistive component and capacitive component. It goes into source top, which is actually here. The source top is connected to source button because this low side switch is turned on, and the source button is also available here. So we have constructed a current path. The diode is important because in the other cycle of switching, a negative voltage will be observed on this diode, and it has to withstand with that voltage. The resistive component is just here for minimizing, for actually limiting the charging current of this capacitance. And during the turn on moment of the top side, high side or the top side switch, the current is supplied by this capacitor to the MOSFET gate structure. So here a question comes for you. We had investigated the profile of the gate current, and it is in shape with impulse type. What I mean is that it goes to several amps in small amount of time. So the question is that an impulse type current can be supplied only by an inductor, a capacitor, a resistor. Which one of do you think is correct? Okay, the answer should be a capacitor, because an impulse type current cannot be supplied by an inductor, because actually the inductor smooths the current, and a resistor is not a supply of anything, it just consumes a real power. So the correct answer is a capacitor, and it was actually shown in the previous page with this high side bootstrap capacitance, which was supplying the current for the high side switch. Okay, the ideal circuit is works without any inductances. However, this is not practical. In practical, we have some gate inductances, which is called as actually the gate loop parasitic inductance. This inductance is caused by the distance between this power source and the gate driver, or this is the inductance is caused by the distance between this gate driver to the MOSFET, our switch, or the IGBT, or the width and thickness of the traces for carrying the current of for carrying the gate current also causes some inductances, and these are the main reasons of this inductance, which causes some problem, as we will see now. These problems should have been solved by placing a proper high frequency capacitor, as it was in the case of bootstrap. This capacitance should be able to supply the impulse type current in small amount of time. So in general, we are using a ceramic capacitor for this type of usage, and these actually gets charged through this voltage source with small amount of time, with small amount of current. However, it supplies the immediate current requirements to the MOSFET to activate its gate. The gate ringing, the oscillations on the gate, might cause a Miller turn-on. I would like you to search for this Miller turn-on, which is a very important concept actually, and it causes some oscillations on switching current, because our MOSFET's conductivity is dependent to the gate source bias level. If this bias level oscillates, this means the conductivity oscillates actually, so the drain current oscillates, and it causes very strong electromagnetic radiation, which causes some EMI or EMC problems for other type of circuits in our converter. Also, the increased oscillations increases the switching losses as well. So in short, we always recommend you not to underestimate the gate oscillations, because most of the time they are the main source of the problems. Okay, as we discussed before, there was some oscillations on the drain source voltages of low side or high side switch if we place an inductance on the power loop. So we had discussed that these oscillations can be solved either by gate driver or a snubber, or we said that let me write here, the inductance minimization is required for solving these problems. So how are we gonna solve these problems with the gate driver design? The answer is actually the gate resistors. So in order not to turn on or turn off the high side or the low side switch instantaneously, we actually put some resistance to create an increased time constant between the input capacitance of the MOSFET and the gate resistance. So in this way, actually, you are increasing the conductivity of the MOSFET slowly, or you are reducing the conductivity of the MOSFET slowly, which means that you are actually turning on or turning off this switch in longer periods. And as a result of this, we are observing a voltage reduction. Now it is as seen below the 100 volts for the low side or the high side switch as well. We can solve this problem. However, we want actually to turn on and turn off our switch with different speeds. It is required to use our switching cycle in an effective way. Let me explain this concept. So let's say our high side switch is turned on with some gate resistance in a slow manner, and it's turned off in a slow manner as well, and it goes like that. At the same time, our low side switch gate source bias voltage is turned off. It stays at the low position, then it turns on, and it goes like that. So actually by slowing down the transition, we are actually reducing, we need to increase the dead time between this turn on and turn off instance. So this means that we are reducing the usage of our the effectively usage of our primary duty cycle. In order to prevent this concept, we need to change the turn on and turn off speeds for high-end low side switches. So we actually want in general to turn off in a faster manner with this type of change for the high and low side switches. So what we need to do for this type of change is that to change the gate resistance for turning on or turning off. In order to do that, we are placing a turn on resistance just connected to output of the gate driver and the gate pin of the MOSFET. The turn on resistance is the only way to carry the current for charging the input capacitance of our MOSFET, CGS, let's say. It's connected to here. However, when it comes to turn off, the diode gets activated. So actually we are paralleling these two resistors, and this causes a significant reduction in the turn off period, which means that we are able to use our switching period in a more proper way. Okay, however, in general, we are using a gate driver with two outputs, the positive and the negative output. So we are actually connecting the turn on and turn off resistors to that pins separately for turning on or turning off our switches with different durations. So this is the actually real case application example. Another important concept mostly ignored by the new designers are the pull-down resistors, which are actually not working in our gate driver circuit in an active way. However, they are required to eliminate any risk of simultaneous turn on of our high side and low side switches. What I mean is that we have a half bridge here, and the gates are assumed to stay as low. However, we are providing some isolation for the high side switch, which means that due to this isolation, this can be triggered by another source on our circuit or another interference with the environment. It can be turned on if we leave that pin as floating point in order not to cause a failure of our circuit. We always provide some pull-down resistors, which makes the gate connected to the source, and it eliminates an instantaneous charge of the gate capacitance, CGS, because it is in parallel with this capacitance, and the capacitance can be discharged through this resistive block. And we also need to provide some pull-down resistors to the output of microcontrollers, because sometimes manufacturers provide some pull-down or pull-up resistors, but we need to strengthen pull-down situation with an external resistor as well, but I recommend you to follow the recommendation of the manufacturer of the microcontroller. Okay, the actual circuit includes more detail than it is seen in the simulation. This is an example layout design of a half bridge, and the high and low side switches are driven with the same gate driver, which includes an isolation inside that gate driver IC. So let me describe the pins of these MOSFET pins. These pins are the drain pins here as well, and these lower two pins are the source pins, and we have a gate pin on the top, and this is the SS pin. The middle one is SS pin, which is called as the Kelvin source actually. Let me draw the symbol of this MOSFET as well. Drain, source, gate. So the manufacturer provides another pin which is called as the Kelvin source or the SS pin, and it is connected to the source pin, but we are using this SS pin just for driving the gate signal. The main current should flow through the drain to source. So the SS pin is actually connected to the gate driver plane. So let's figure out how the current is supplied, but first let me define the circuit components in a better way. This is our microcontroller. Okay, this is our microcontroller, and this is our gate driver IC connected to high side and low side switches. This is our turn on resistance. Let me write it, turn on, and this is our turn off resistance. So let's clear this screen and define where the current flows for a turn on instant. Okay. The current should be supplied for a turn on. The capacitance between the gate to SS pin need to be charged, so the current goes inside this pin and comes to the outside. So as I said before, this was the turn on current, so this current comes through that pin, which is supplied by this pin of the gate driver IC, and this current should have returned back to our gate driver IC as well. In order to minimize the inductance and the resistance, the designer provided a white region, a copper region, for minimizing the inductance and the resistance. And note that this region is just placed below the topside coppers. So the current goes with the vias to the other layer. The current goes to the other layer with this vias and comes back to the layer where the soldering is made, and this current goes inside the gate driver IC. However, the impulse type of current should have been supplied by a capacitor, as we discussed before, and this capacitor here, this capacitor is placed here. It is placed in a very close manner to the gate driver IC, as it should be should have been done. So actually the path for return current is not correct. So the correct path should be like that. The current coming through the SS pin or the source pin should have gone to the capacitor, because that is the main supply of our gate driver current, and this current comes through these capacitors, goes inside the gate driver IC, and is supplied through that pin for turning on moment. And the similar thing happens for the turn off moment as well, but the most important thing is that let me clear once more. Okay, let's clean them as well. Okay, I would like to draw with a different color. The gate driver capacitor and the gate driver IC are very close to each other. Moreover, our switching component and the gate driver IC is also close to each other. A separate turn on, turn off resistors are included. A white traces are placed to minimize the inductance. Moreover, for returning current, a copper region is placed to the bottom layer, and this bottom layer copper plane is placed just beneath the topside tracks. This is the way of minimization of inductance for the gate loop. And as you see, for the low side switch, this is also valid as well. Okay, as we discussed in the previous slides, in order to drive the high side switch, we need to provide the isolation, because the PWM signal is supplied by the microcontroller, which is in reference with the low side switch. So we need to construct a galvanic isolation between the high side switch to microcontroller. In order to visualize this concept, let me draw that circuit in an easy way. Okay, this is our ground. So this is our gate driver IC for the low side, and this is our microcontroller unit, which is actually connected with the same ground of the power supply. So this can be connected directly to the low side switch. However, the gate driver IC of the high side switch has to be isolated from microcontroller. This is the isolation barrier, and we need to carry some power and the PWM data to the other side. So actually we are using these isolation components either to transfer power or the data from one reference level to the another reference level. So there are ways to construct this isolation, and the most common ways is having an inductive or capacitive isolation. For both of the situation, they always conduct an AC signal, not the DC signals are conducted through these isolation components. The flux created on the primary side coil is actually coupled with the secondary side coil. So whenever we apply an AC signal, it causes another voltage induction on the other side, and the AC signal comes to the primary side and goes to the secondary side. And as we discussed for the gate driver, the gate structure of the MOSFET, the capacitive couplings are also able to carry the current for AC signal. Here the isolation barrier is shown, which is the silicium oxide between these two conductive layers, and we can carry the AC signal through that capacitive isolation as well. Another way, which is actually has the same theory with the inductive coupling, the RF isolation. We are seeing two micro antennas for receiver and the transmitter, and we have constructing some chirped signal on the let's say the transmitter antenna, and it is coupled with the receiver antenna, and this data is transferred with the isolation to the other side in this method. Another method, as we said, is the capacitive isolation. The DC current cannot go through the isolation barrier. However, the AC signal can be transferred. Let me write here. It is DC and this is AC through the capacitive barriers. And this is the configuration of it is die. The capacitance are here connected in vertical way. This is the isolation barrier between the two sides, and we need to pay some attention to these isolation requirements. But first let me show other type of isolation component. This is a pulse transformer, which actually has a PWM signal input. When it is in the steady state position, it does not cause any change on the state of secondary side. However, whenever a DVDT occurs on the primary side, we see an impulse on the other side, and this sync signal can be coupled with another IC, and this can be converted to a turn on or turn off signal with that IC as well, and a pulse transformer schematic circuit is shown on the below. Okay, another widely used isolation type is the optocouplers. which are actually transferring the data with the lights, the LED connected to the primary side illuminates the inside of the package, and the light sensor detects this information, so it provides an output current based on the strength of the illumination on this LED. So it is actually suitable for carrying an analog or digital data from one side to another side. So another thing we need to put some importance is the PCB design for isolated structures. Here are two examples. We are seeing a transformer for the which is connected between the primary and the secondary side, and also it is available for that PCB as well. However, we are seeing for both of them the optocouplers are placed from primary to secondary side to carry the regulation data from secondary to primary, and we are seeing the isolation barrier distance between these two isolated copper regions, and we need to provide some clearance region between these isolation paths, otherwise it constructs another capacitive path to carry the current, and this path can distort our signal for analog measurements or digital PWM signals, etc. Okay, the manufacturer recommends a layout design for the isolation, and it says do not put any copper between these two isolated copper regions for any layer. So we need to take this into account. It is not even possible to place a copper to the other layer of the printed circuit board. This region should be kept as clear as described in this image. Okay, another important terms are creepage and clearance. Clearance is defined as the minimum distance between two isolated components, and the creepage is the distance of the surface between these two components, the length of the surface. Whenever a failure occurs between these two components, the surface is coated with a carbonized item, and it is conductive, and it increases the failure of the circuit. I mean, it causes a burn over the whole circuit. So in order to prevent this kind of failure, we provide the creepage distance increased, and clearance distance should be also set with respect to the isolation standards. So this is the end of our lecture. Thanks for your interest and watching.